Hello, welcome back. Today we'll be talking about modeling abstraction. So we have a few more key concepts that we just need to talk about so that the terms are clear for everybody and that we're all on the same page. Let's get started. So we'll look at software development processes, we'll look at design processes, we'll look at models and modeling, and we will look at abstraction. So we will start with the oldest one, waterfall development process. It is kind of not real development process because in its pure form, it would be the anti-way of how to develop software. So you see there are consecutive phases, one after the other: requirements, design, implementation, validation and verification, and then maintenance. However, you can't really move in such a sequential way, which means this model makes only sense if we actually add some feedback loops onto the individual phases. Because otherwise I would have to know all the requirements at the very beginning of my process. And it's been many decades since we've done that, since we did know those so far ahead of time. So I put it in here for completion. It's not something that is really in use in this way, but it helps to derive the other models from it. For example, the V model. So the V model emphasizes system quality throughout the development. You start with analysis on the left, then move into a design phase, then have the implementation at the bottom of the V. Then you move into several phases of testing: unit testing, integration testing, system testing, and acceptance testing. So in each of those testing phases, you refer back to what had been specified on the left side. That one is used a lot in automotive design, for example, but also in different other areas of the industry. And then we have a whole set of iterative models. And the basic idea of those is that after a general planning phase and a general analysis phase, you go into analysis, design, and implementation of system version 1. And then you do an iteration and do analysis, design, implementation of the system version 2. And then you do the same for system version 3. The iterative model allows you to expand a system over time, and that's how it became widely adopted. And then there is several other process models that we're not going to look at in detail. It's more to get you back into the groove of thinking about software development processes. So we also have prototyping, we have, of course, agile development, and then we have a lot of hybrid models in between all of those. So there is very few companies that practice agile to the extreme. There is many that kind of integrate agile with an iterative model that do some kind of hybrid approach. So we want to have our basics down in those. Make sure you read up on them a little if you do not remember a lot on them. What we're going to move into today is what is system analysis. So the main idea is we need to identify the main concepts in a problem domain and their interrelations, so we can describe that domain through models. That includes eliciting and understanding requirements and a scoping of the system context, both of which we're going to do in the next module of this course in detail. What's modeling? Model exists both as a noun and as a verb. As a noun, it's an abstract representation of something. Models focus on the essential. So here you could say, you see a model of me on the slide, because it's a stick figure of a human. So it has a face, it has a smile, it has 2 eyes, it has 2 arms, and it has 2 legs, which you can't see right now. And you can also use it as a verb. Then it refers to the process of creating a model, choosing what to present and how to represent it. So for example, which notation you're using. And as very clear in this example, it's using the stick figure notation. A couple of other examples. Here is a model of Göteborg, which you can see at the university. So you can walk through there and you see all the elements of the city. The brown buildings are the ones that already exist, and the white buildings are the ones that are planned for the future. So it's a model that is not even just representing the current status, but also looking pretty far into the future. And at the same time, downsizing quite a bit because the entire city fits into one room. Another example is DNA. So both of those models look fairly different. They do represent some same concepts. And so here we already see, oh, what are some of the things that may mean a lot for modeling? Like it has something to do with not representing every single detail because the left one is clearly abstracting from more details than the right one. It also means I reduce somehow to the part that is most important. So on the left side, it seems that those little antennas that are sticking out on the right were not really important for the representation of what they wanted to show for the purpose of using that model. On the right side, those were important. Another example would be a global climate model. This one is taken from Wikipedia. So while we know that it's not as simple as that picture down to the left, it gives you a general idea of the main concepts involved in global climate. I already started pointing out, wait, that city model, it's not an original size. So the giant big city fits in one room. So all models are abstract and simplified in some way. And there's this beautiful quote of the statistician George E.P. Box, who said, essentially, all models are wrong, but some of them are useful. And what he means by that is, you know, if you look at a particular model, say that picture of the city model of Göteborg, then you could say, well, this model is wrong. The windows, they are not, there are no windows in the buildings, there are no doors. Like this model is wrong. It's the wrong size. But useful, it can still be. Like it's useful because you get an overview of the entire city plus a view into the future. And so it is useful for that specific purpose, but only for that purpose. It would certainly not be useful to put it, for example, into a travel magazine to advertise for tourists coming to Göteborg. So the question for all the models that we deal with is, what is the particular purpose of the model that I'm looking at? Or which model do I need to choose for a particular purpose that I need to fulfill? And the purposes of these models can be quite a few. So from understanding, managing complexity, which means in my own head, if I think about the design of a fairly complex software system, say I want to invent a new social network, I'm not going to be able to have that whole architecture in my head, that whole design. It's way too complex. So to help me break it down in my own head, I can use models to help me think through things. Then I can use it for communication. So I can create a shared understanding and representation. So I can discuss with a team. So I can explain to stakeholders what is going on and how the design works. Then we need it for implementation. We need it to guide the construction of a system. And often we can use it to generate an implementation by code generation. And then we get to the analysis part. So we can verify if the design meets the requirements, but also later on, we can verify whether the system follows the actual design if we have documented it in proper models. So the word design has been used a lot, but what's the meaning of that one? So we can use that one as a verb and as a noun as well, like model. That's a bit of a pitfall, I know, but we can work with it. So design as a verb means the process of making decisions about something that is to be built or created. And the design as a noun is the outcome of that, the plans, the drawing that show how something can be made. Now, modeling and design do usually go hand in hand because a model is used to understand, to reason about, to analyze, to break down, and that leads to an adaptation and refinement of the design. So the model is the representation and the design is really the construction plan in the background. Now to do that, we have several diagram types that we can work with. And in this particular course, we'll only be using UML diagram types. There are structural diagrams and there are behavioral diagrams. So the structural ones are the ones that give us a way to show the elements that make up the structure of the system. And the behavioral diagrams are the ones that, that show us how things happen in the system. I'm not going to read through all the individual diagram names. We're going to be using a large share of them throughout the system, throughout the course. Systems, there we go with the systems. They have multiple aspects. So you can see that there are these different models here for a house. The house itself, the thing we want to build, is in the middle. And then we see there is a support structure model. There's a plumbing plan. There are floor plans. There's an electrical plan. And there's an exterior covering model. So all of these models are valid models for the same house, but none of them would represent all of it. We need all of those different views to be able to understand the house and to really build the house. And what we need for making those several models are some key concepts: abstraction, generalization, classification. I'm going to start with abstraction. Abstraction extracts the essence of a concept. So we're going to exclude some of the details. In the Göteborg city model, we excluded the details of, say, windows and doors, for example. We generalize. You won't see the different colors that the walls of the houses in the city have. They all are the same. They all are brown if they exist, and all are white if they don't exist yet. And then there is classification and grouping going on. So you see that all family homes may have pretty much the same shape and size, same as all apartment buildings, and you kind of group them together. And we use these abstractions to make things a little simpler and to avoid artificial dependencies on the implementation details, on the hardware-software details. Because if early on I was already specifying, oh, we're going to connect that to this and that type of bus or to this and that type of sensor, then as soon as I have to change something in that hardware design and maybe have to change the type of the sensor that I'm using, that would mean that I also need to change my software design. Now that would really suck on a high level. That would make maintenance effort incredibly complex. And because we're trying to ease that, we use abstraction on different layers to deal with one problem at a time. There are a couple of different visualizations I want to give you for abstraction. One of them is according to Picasso. I hope you know him. That gentleman is a Spanish painter and artist. And if you don't know much about him, go look him up. Fabulous, fascinating. Most of his lifetime he lived in Malaga in the south of Spain, where I happen to live half a year of my life. So I'm fairly familiar with his artwork and I very much enjoy it. He was an exceptionally good painter in terms of painting physical objects and reality exactly as they were. However, he found over time that that was not that interesting. So he started playing with it. He started abstracting. He started to think about what are the key elements that really make a bull a bull. And you can see the progression over time. And you can see how he played with different elements until at the very end, at the bottom right, he came out with the most reduced version of what he considered was still easy to recognize as a bull. Another example would be the London Tube. Thanks for Michel Chaudron for pointing this out. So on the left, you see a map of the underground railways of the London Tube. There were about 50 stations at the time. And you can see the map is still somewhat correlating with the actual city map at the time. Now, if you look on the right-hand side, you have more than 250 stations, and that is not even the whole map. That is an excerpt of the map. So you have 250 plus stations, and there is very little resemblance with any GPS coordinates that may actually be valid for this map. And then last, computation. we often speak about the black box of the computer. So we have some kind of input into the computer that can be a user input or that can be a sensor input, and we have some kind of output, some kind of response that gets triggered. And internally, there's usually a type of function that will turn the input into output. The question with abstraction is, how do you find the right level of abstraction? If you make it too abstract, everything looks like an input goes to output problem, and that will often not be sufficient for analyzing a problem. If you go too detailed, you may be dealing with too many dependencies, like the dependency on a specific hardware sensor that I was mentioning. Or as you see illustrated, if you have a pierced heart on the left, that looks like a fairly realistic heart that was just ripped out of somebody else's chest. In the middle, you see an icon that is fairly recognizable to everybody, what it means. And on the right-hand side, you see something that is too abstract to really recognize because the heart is abstracted into a red square, and it's not understandable anymore as a pictogram. So the challenge is always to find the right abstraction for the problem that we're looking at any given point in time during a design process. And that's one of the things that we're looking at this course. What's the right level for that? Now, what we design versus how is also really important. What is the more analytic part at the beginning? It's declarative. We're talking about the problem domain. What kind of system environment are we dealing with? What are the requirements? What does the interface need to look like? And then on the how side, we look into the black box, so to speak. So we talk constructive. We talk about the solution domain. What is the implementation going to be like? And what is the algorithm? An example for that would be the what is, I want to move myself from A to B. I want to get from Göteborg to Stockholm. How is fairly open. I could take a train. The train is very quick. It's convenient. I can do some other things while I'm riding. I could take a car. I could probably ride on a truck. It would take me pretty long on a bicycle. There are certainly buses that go. On a skateboard, it would take me a very, very long time. Also, I would probably face plant because I'm not a good skateboarder. By boat, we might have to go a very long way around. That seems fairly inconvenient. And airplane is certainly very fast, not quite as fast as the train if I account for the time that it takes me to get to the airport and back from the airport, and also is not as environmentally friendly. So there's a lot of options on the how part. The what part is fairly straightforward and clear. That is often a fallacy though, because it's not always as straightforward and clear. If I am not entirely sure, if I'm not talking about myself moving from A to B, but about a stakeholder that I need to satisfy, then there are probably a ton of side constraints that I should know about. For example, timing constraints, or where exactly they need to be in the city, or for how long they want to stay, or how much money they can spend, or what emissions they are willing to spend on this. So there's often a lot of extra information to be gathered that we need to learn to ask about. And a lot of that is done in requirements engineering. However, we need to be conscious to revisit some of that during the analysis part for software design, because there were often some things that in the initial requirements elicitation were not asked or did not come up. So you're not off the hook yet for that one. We go back to talking to stakeholders. Now, one more thing that I wanted to bring up, because it ties this how and what in as well, is design thinking. So we start out in the context where we define a why, like why are we doing something in the first place? We create a point of view based on user needs and some insights that we had. And that is only possible once we've understood for who this is. So messed up, we start with the who, of course. So we need to empathize and understand the human needs that are driving a certain design need. And often somebody will jump in with a why and a what, And then we need to work backwards from there till we get to the empathize. But anyway, starting from the empathize, the who, we move on to the why, and then go on to the what and develop a couple of ideas. And then we go into the how and prototype that. That's where we're in the solution domain. And then we have to test that and get feedback from our users, from the who, from the stakeholders. And we will iterate this whole process based on that feedback. That means we need to go back into empathizing. We need to go back into understanding why they particularly like or dislike a certain aspect of our prototype. And then based on that, we adjust our why and develop new ideas or improve the existing ideas, and then prototype those again, re-prototype, and then go through another testing loop. So that's how the how and the why and the what are really tied together in figure eights. Now, another thing that we see a lot in software development is layering as abstraction. We talked earlier about the hardware design and that we often want to abstract from that in our software design so we don't create more dependencies than necessary. Which means if we start with the physics and then move up to devices, gates and registers, and then to microarchitecture and instruction set architecture, that's where hardware meets software. And then we move on into machine code, assembly code, programming languages, algorithms, and finally applications. So I'm really curious who of you has actually dealt with machine code and assembly language. When I studied, I don't want to say how long ago that was right now, never mind. I still did a little bit of both of that, of machine code and assembly language, and I think it's really helpful to understand how all of this breaks down. I know by now it's not done in all curricula, and it's fair enough because we only have so much time to spend. And we need to focus on whichever topic is most important to us. However, if you look at that stack, and then you get a pretty good understanding for why we want to make sure we create enough abstraction as we work on application or algorithm layers. Because if we have to deal with transistor problems, with transistor dependencies on the programming language level, that would be horrible. Like, there would be so many dependencies. Every time we want to change something on the transistor level, there would be so many dependencies in the programming language that we would never get any software out the door. So therefore, that abstraction, a principle of abstraction, is crucial to making good software and to making good design. Now, the last one that I mentioned was classification. No, second one, sorry. Classification, and a little example here is classifying animals. So we're trying to classify, group together what things, specific things have in common. And for animals, you can understand that there are reptiles that all belong into one group, like the crocodile, the snake, and the chameleon, and the tortoise. They all belong into the group of reptiles because of the type of skin they have and because they're cold-blooded. And then you can look to the birds. The birds all have wings. Some of them are great at flying, some of them are not so great at flying, but they all have wings, and they're covered in feathers, and they have scaly legs and beaks. So you have some of the vertebrates, and then you have all the invertebrates. And I really enjoy this chart. I also know this is not a lecture about animals, so I'm going to hold myself back and move on through this. So you get it. Classifications are useful for abstraction. Another thing that is useful for abstraction is generalization. So when we look at different modes of transportation, for example, an automobile or a motorcycle, those could be generalized to types of private vehicles. And then we see the bus or the semi that are both commercial, and those private and commercial vehicles could still be generalized into land vehicles. And then if we look on the other side, there are a couple of different types of aircrafts. And if we look at all of those on top, then we can generalize that to vehicles. However, generalization, there are some fallacies possible. And I think most of us might be able to find a point in our life where we've made some kind of hasty generalization. And when this little Birdie has said, that monkey stole my banana, therefore all monkeys are thieves, then he is falling for a hasty generalization. It happens when people jump to conclusions with too little information, because you can't really judge all monkeys based on that one naughty monkey's actions. All right, back to key tools. Classification, abstraction, generalization, they are all key tools for us as analysts and as software designers. And if you like Star Wars, I do, maybe you can just keep Yoda in mind. Clear your mind must be to see the pattern in the complexity. It rhymes, and what rhymes is good. Don't mind me. If you find this ridiculous, that's fine. I promise you it's going to stick a little better. So clear your mind must be to see the pattern in the complexity. With that, here's a little overview of the models that we will deal with. So on the left, you see the analysis models, and on the right, you see the design models. The analysis models are scenario-based, flow-oriented, behavioral, and class-based, and all of these can then be transformed into design models at an appropriate level of development. And in a different depiction, all of this is a superset for our course, so don't worry, we're not going to do all and every one of these. But at the top, you see the analysis model and all the things that you can use within an analysis model. And at the bottom, you see what goes into the design model. And then you see this dimension on the left that says abstraction. So it's really important that at the beginning, you have more abstraction. You abstract from the how. You really talk just about what are the things that need to be represented and what are the things that need to get done. And then in the design models, you talk about how are they going to be represented and how are they going to get done. Now, what have we looked at today? We've looked at what is a software development process, what is analysis, what is a model, and what is it not. Why do we model? What are purposes of models and what is design? How do analysis and design relate? What is the relation between software design and the general design process? And what are abstraction and generalization? In the last little intro, I said there will also be another recommended reading, and it's Software Design Decoded, 66 Ways Experts Think. I promised you 100. I was wrong. I misremembered. The book was written by Marianne Peter and Andre van der Hoek, and it has a lot of really useful habits and best practices that they have observed over many years in thousands of software practitioners and thousands of experienced designers. And we will use a few of them in this course because it will be overwhelming to throw all of them at you. But if you're interested and if you like those examples, I strongly recommend getting that little book. It'll help you out for a long time. I look forward to seeing you next time. Please post any questions you may have below. Please post comments, leave feedback, and thanks for watching.